All right, these are going to be problems from the 2009 AIME number 1. This will be problem number 1. If you want more AIME content, please leave a comment down below, give it a like, do something so that I know that enough people want AIME content, and I will try and do more AIME content now that this year's tests are over. Thank you. So 2009 AIME 1, problem number 1, call a 3-digit number geometric if it has 3 distinct digits which when read from left to right form a geometric sequence. Find the difference between the largest and smallest geometric numbers that are 3 digits, I would assume. So then how can we find this? If you want the largest one, you probably want to start with 9. Right? So something has to be starting with 9 to be the largest, that's 900s. Now, in order to be geometric, I have to be able to multiply 9 by something. It can't get bigger, of course, because there's no bigger digit than 9, so it's going to have to get smaller. Now, I could multiply by 1/3. Only 3 goes into 9, or 9 goes in as well, but if I make 9 go in, I'll be at 1, and then the next number has to be smaller than 1 and be like 1/9. You can't have that. So then we have to make 3 go in. Now it is true that 3 can go in and give you 3, and then 3 can go into that and give you 1, multiplying by 1/3 every time. But why multiply by 1/3 when you can multiply by 2/3? Because 2/3 is bigger, it'll leave a larger number. So 9 times 2/3 is 6 times 2/3 is 4. This is clearly the largest one. Now let's start with the smallest one. We want it to start with 1, and you want the smallest multiple as possible. We can't have a fractional multiple this time because we'll get a fractional number, which isn't a digit. It's not going to work. So we take the smallest integer multiple we can use, which is 2. So 1 times 2 is 2. 2 times 2 is 4. Now, double check. It also said 3 distinct digits, which means we couldn't have done 111 times 1, for instance, or 999 for that matter. So this is it. 964, it wants the difference, so we subtract. You're going to get 840, which ends up being the answer. All right, continuing on, this is the 2009 AIME number 1, problem number 2. There is a complex number z with imaginary part 164. Well, let's call z then a plus 164i. That's the imaginary part. This is the real part. And a positive integer n. So the positive integer is not imaginary. It's a real number because integers are real numbers. Such that z over z plus n, so I can call this a plus 164i over a plus n plus 164i. Because this plus n, you can group the a and the n together because they're both real numbers. Okay, so then this is equal to 4i. Now you have some options at this point about how you want to progress. Keep in mind, by the way, you have an average of 12 minutes per question if you're going to answer all 15 questions. So try not to rush too much on the AIME. Just give it a little more thought, a little more time. Make sure your answers are correct. There's no multiple choice, of course. You just have to provide the answer. The answer ranges from 0 to 999 as a reminder. Okay, so we could multiply this by the conjugate of the denominator on top and bottom, but that's probably going to get a little messy. What if we just swapped these two? If you have a over b equals c, then you can make this a over c equals b. That's okay. You just multiply by b and then divide by c. We can do that here, and we will get a plus 164i over 4i equals a plus n plus 164i. Now, we can divide this 4i into both of these terms to get a over 4i plus 41 still equal to that expression. We just continue on. You don't want a denominator like this. There should be no I in the denominator because there's no I in this denominator. So let's multiply by I over I. The I squared is -1, making this negative a over 4i plus 41 equals a plus n plus 164i. Now, we can see then that the real parts have to be equal and the imaginary parts have to be equal. So this imaginary part of negative a over 4 has to equal the 164 over here. Multiplying by 4, we get negative a equals 4 times 16 is 64. Throw a 0 on the end to get 640, and then 4 times 4 is 16. 640 plus 16 is 656. If you're not sure what we did 4 times 160 plus 4. Okay, then I'm going to move the negative over to get a equals negative 656. Okay, now we just need to come over here. This 41 is the real part, and it has to equal the other side's real part, and we know that a is negative 656. So 41 is equal to n minus 656. We simply add the 656 to both sides, and you will get 697, which is what n is equal to, and is the answer. All right, continuing on, this is the 2009 AIME 1 problem number 3. A coin that comes up heads with probability p greater than 0 and tails with probability 1 minus p greater than 0, so it's not an equal chance, independently on each flip is flipped 8 times. Suppose the probability of 3 heads and 5 tails, so probability 3 heads, 5 tails, is equal to 1/25 the probability of 5 heads, 3 tails. Let p equal m, not this p, that's just stands for probability. Let p equal m over n, where m and n are relatively prime positive integers, and then do something with m and n, right? We get that. The ending, when you get to the ending, don't read it actually when you're doing the test. This part here where it says let p equal, all of it's just going to be a generic statement about something to do with a fraction and relatively prime. We don't care about that right now. You should care about that after you find p. Make sure p looks like what they say then, and that they're relatively prime, and then do what they say. Okay, so how are we going to do this? Actually, there's only 2 outcomes, heads and tails. And when there's only 2 outcomes, we get to use a tactic called binomial probability. In the future, I'll probably make a video explaining binomial probability. Leave a comment if you would like that sooner rather than later. But for now, I'll just give you the formula. So the formula works like this. It's n choose k successes. I want k successes from n trials. So for us, n's going to end up being 8. And we can consider success whatever we want, heads or tails. In this case, I'm going to consider it heads with probability p. So after we say how many successes we want, you're going to multiply that times the probability value, what the probability is for heads, which is p, but to a power of how many successes you want. So we'll get to it in a second. It'll be p to the k power. And then also times 1 minus p to the difference in these 2 numbers, n minus k. Okay? If you give it a little bit of thought, it's kind of intuitive why it works. But again, if you want, we'll go a more in-depth explanation in a future video. I just don't want to do it in the middle of solving the test. Okay, so n choose k. How does this work then? We want it to come up 3 heads and 5 tails. Then I want, out of my 8 trials, I want 3 of them to be success, which we're calling heads. And then heads has probability p, and the k is this bottom number 3, right? And then 1 minus p needs to be what's left. 8 minus 3 is 5. Okay? This needs to equal 1/25 of the probability of 5 heads and 3 tails, which we're just going to use this same thing again. It's going to be 8 choose 5, because I want 5 successes this time, and I want p to the power of 5, and then 1 minus p, the chance for tails, to the 3rd power, which is also the number of tails you want, which is why you're subtracting. Okay. From this point, we simply have to solve. Now we're going to use an idea from combinatorics. If you've qualified for the AIME or if you're close, you're watching this video, you probably already know this. But whenever you have a combination and the bottom numbers add up to the top number, they're actually equal, right? This is easy to understand why. Let's just write what 8 choose 3 is. It's 8 factorial over the difference 5 factorial and then the bottom number 3 factorial. While this is 8 factorial over the difference 3 factorial times the bottom number, they're the same thing. So because of that, and because we have the equal sign, these just cancel. We can be done with those. Okay, next up, you might be tempted to distribute this in binomial expansion. That's not a lot of fun. Let's avoid that because we don't want to do it. When you sense pain on the test, well, usually, a lot of times when you sense like pain of calculation stuff, there's probably a shorter way, so you should think about it before you progress with the painful path. Okay, so what we're going to do is just divide. P cubed divided on both sides is going to leave p squared over here. P to the 5th divided by p cubed, right? Cancel, cancel, p to the 3rd, this leaves p squared. Similarly, we're going to divide by 1 minus p cubed, and it will cancel over here and leave squared over here. 1 minus p squared. Great. Now we can just, expand this. So we've got 1 minus 2p plus p squared equals 1/25 of p squared. We can go ahead and multiply by 25. You're going to get 25p squared minus 50p plus 25 equals p squared. This p squared that's still there after you multiply by 25. Now move it over here to get 24p squared minus 50p plus 25 equals 0. Now we have to factor. Now the thing is, there are many ways to learn to factor complex factorizations. I have a preferred method. If you'd like me to teach that in a video, please request it in the comments. I'll make it as soon as possible if I get enough requests. The way that I factor is you're just going to write the factors of 24 next to it. And there's a bunch of options. It could be 24 and 1, 12 and 2, 8 and 3, 6 and 4. Those are all options. Usually, not always, but usually it's the ones that are closest together. So take this 6 and 4 for instance, and 25, it's probably not the extremes of 25 and 1, it's probably 5 and 5. Now what you're going to do next is you multiply this 6 with this 5 to get 30. And you multiply this 4 with the other 5 to get 20, and see if those numbers, 30 and 20, can make this middle number by either adding or subtracting. In this case, we only want to do it by adding because I have to have 2 positives or 2 negatives to make 25. So when I add 30 and 20, I do get 50. We're good. This is going to work. What are these 6 and 4? Ultimately, it's 6p and 4p. It's the coefficients of p in the two binomials that you're going to factor. And what are these 5 and 5? They go on the ends because they're going to multiply to make 25. The last thing that I put in is the sign so I can think about it one more time in case I made a mistake. Again, if I use 2 positive numbers, this will come out okay, this will come out okay, this won't come out okay. So I need 2 negative numbers, because a negative times a negative will still give the 25, and I will get negative 30 here and negative 20 here. That 30 and 20 we talked about, that's the 2 middle terms, and they do combine negative 30p and negative 20p to make negative 50p. Again, if you want me to explain that in more detail in a factoring video, request it down below. I will happily do so with many examples, not just this one. So then, solve to get p equals 5/6 or 5/4. Now let's think about it. It's a probability. Probability ranges between 0 and 1 inclusive. Then it can't be 5/4. So that one's out. And the answer is p equals 5, not the answer, but the answer to our little problem here is 5/6. Now we come and look at the last sentence. This is when you think about what they wrote here. You don't need to worry about it before. Let p equal m over n. We have an m over n where m and n are relatively prime. Again, relatively prime means they have no common divisors other than 1. Positive integers. 5, nothing goes into 5 that also goes into 6 except for 1. We're satisfied. What do? We add m and n, and you get 11, which is the answer.